In this video, we analyze the conditions under which a harmonic oscillator can absorb or emit a photon and undergo a transition from one state to another. If you recall, the energies for the stationary states of a harmonic oscillator are En equals h bar omega times n plus 1/2, with the oscillator angular frequency omega equal to k over mu, square root of that, and n equal to 0, 1, 2, and so on. N is the vibrational quantum number. The energy level diagram looks like this. We plot the energies scaled by h bar omega. The lowest level is at 1/2 h bar omega, that's n equals 0. The next one is at 3/2 h bar omega for n equals 1, and the n equals 2 level is at 5/2 h bar omega, and so on. Now, under which conditions can a harmonic oscillator absorb a photon or emit a photon and transition from one state to another? There are three conditions that have to be met. First condition: for absorption, the incoming photon energy, let's call it E photon, has to match the energy difference between two states, delta E. Let's say between two states, one of them being n prime and the other one being n. For emission, it's the other way around. The difference in energy between two states is emitted in the form of a photon with that same energy. And this is all a consequence of energy conservation. Condition number 2. Photon absorption or emission is only possible if the two states are adjacent. That is, between 0 and 1, or between 1 and 2, or between 2 and 3, and so on. That means the vibrational quantum number is only allowed to change by 1 during the transition. So n prime minus n, which we designate with delta n, has to be equal plus minus 1. These transitions are called allowed transitions. And all others that are not allowed to occur, where delta n is not equal plus minus 1, are called forbidden transitions. The plus in this indicates going from a lower level to a higher level, and the negative sign, -1, indicates going from a higher level to a lower level. So positive is an absorption and negative is an emission. The third condition is that the electric dipole moment of the oscillator has to vary as a function of displacement. Mathematically stated, d mu dx at the equilibrium length x equals 0 has to be non-equal to 0. Mu is the electric dipole moment along the displacement direction, and x is, as usual, the displacement. Let's visualize this rather abstract sounding condition. Take hydrogen chloride, HCl. HCl is a polar molecule with a partial negative charge, negative Q, on Cl, and a partial positive charge, positive Q, on H. If you shine light onto HCl from the side, such that the electric field component of the light wave, E, is in plane with the bond, then the electric field can push and pull on these partial charges and induce, stretching the bond, and thus inducing a vibration. The electric dipole moment of HCl is the product of the partial charge, Q, and the bond length. So mu equals Q times R. Clearly now, if you stretch or compress the bond, the length R is changing, and consequently the dipole moment is changing, satisfying our condition number 3. Now, on the other hand, look at dinitrogen, N2. N2 is nonpolar, and it does not have partial charges. Incoming light, even with the correct polarization, has no handles to push or pull on the atoms and to induce vibrations in this molecule. Therefore, dinitrogen does not undergo vibrational transitions. Let's talk about the origin of these rules number 2 and 3. They both stem from a single requirement. This requirement is about the electric transition dipole moment. Transition dipole moment. Mathematically, this transition dipole moment is psi n prime mu psi n in bracket notation, or in integral notation, integral from negative infinity to positive infinity of psi n prime star times mu hat operating on psi n dx. Psi n prime and psi n are the two wave functions, and you notice that unlike in a normalization integral or a expectation value integral, these two wave functions are different. The operator is the electric dipole operator. And the entire expression is called a matrix element of this operator. The conditions number 2 and number 3 now stem from the requirement that this matrix element here has to be non-equal to 0 for an allowed transition. Now, the dipole moment of a diatomic molecule, mu, is clearly a function of displacement. If you stretch it, the dipole moment grows. We can expand it in a Taylor series around 0, and we get mu of x equals mu of 0 plus d mu dx at position 0 times x plus 1/2 times d squared mu dx squared at x equals 0 times x squared plus higher order terms. Since we are restricting ourselves to small displacements as usual with the harmonic oscillator, we can drop the quadratic and the higher order terms. Now, inserting this expression into the transition moment expression, we get bracket psi n prime mu psi n equals to mu 0 times bracket psi n prime psi n plus d mu dx at position 0 times bracket psi n prime x psi n. I've pulled mu 0 and the derivative out of these two integrals, since both these factors are independent of the integration variable x. Now, the first term contains an overlap integral between two orthonormal wave functions. It is 1 if the left and the right wave function are identical, but it is 0 if the two are different. So since we're looking at transitions, which are automatically between different levels, this entire expression is 0, and we can drop it. The second term contains two factors. The first is the derivative. If it is 0, the entire expression is 0, but it should not be for an allowed transition. So this is the origin of selection rule condition number 3. The second factor is an integral. In order to solve it, we need to insert full expressions for the vibrational wave functions psi n prime and psi n, and then simplify. The wave functions contain Hermite polynomials. We can make use of a recursion relationship between Hermite polynomials, and after a bit of work, it turns out that this integral equals to 0 unless n prime equals to n plus minus 1, or in other words, delta n equals to plus minus 1. Now this is exactly condition number 2 of the vibrational selection rule. In summary, a vibrational transition is allowed if 3 conditions are all met. First, the absorbed photon energy matches the energy difference. Second, the transition occurs between adjacent vibrational levels only. And third, the dipole moment of the molecule varies during the vibration. If any of these 3 conditions is not met, a transition is not allowed.